Okay, we have here today a Laplace transform. It's been a while since I did one, and I wanted to kind of revisit this because a few months back, or I don't know, maybe it was a year ago, I can't even remember how long ago it was, we did the Laplace transform of ln(t). So this is going to be really a very similar method. We kind of, in some ways, we get the t to the a for free, but we're going to do the Laplace transform of t to the a times ln(t). Just for review, we have the definition of the Laplace transform right here, putting it in the form of an integral. If you want some background on the Laplace transform, I'm not going to get too far into it because I've got a pretty extensive playlist, so I'll put that in the description if you want to review or you just kind of want to see where some of these formulas are coming from. One important formula we'll use is this one over to the right, just for like we use this on polynomials, where n doesn't have to necessarily be an integer. We can express this using the gamma function. Also, usually if this is an integer, gamma of n plus 1 can be written as n factorial. One thing I won't use is that formula we found in the other video of the Laplace transform of ln(t). We'll kind of start over from scratch and kind of derive all that again, but you can find that one in the playlist as well. What I want to do first is use that definition we just had up here and write it as an integral. So we'll write this as integral going from 0 to infinity. Our f of t is going to be all this, so it's going to be t to the a ln(t) e minus st dt. And then what I want to notice is if we kind of cover up the ln(t) and ignore that for a second, then what we have left is going to be exactly this, because if you put this in terms of an integral, it's going to be this without the ln(t). So I want to work with this thing. Having natural log inside of a Laplace transform is kind of confusing. There's not like a standard formula for that. So what we'll start with instead is this simpler thing, which is going to be integral from 0 to infinity, t to the a e minus st dt. And we know exactly what this is because we have the formula. This is going to be, just using a instead of n on this is going to be gamma a plus 1 over s to the a plus 1. Then let's kind of label this. I'm going to call this a function. I'm going to think of this thing as a function in terms of a, even though, you also could look at it as a function in terms of s. The reason for doing this is I want to use Feynman's trick on it. I want to differentiate this thing. I think we've all seen this before, so I'm just going to kind of do it on the fly here. But what we want to do is we want to differentiate this, but do it as a partial with respect to a. So then this piece here becomes a constant. So we'll just leave that. Differentiate t to the a using the formula. This is going to be the same thing as t to the a ln(t). So I just did that all in order just to create this thing that we wanted here, because these are identical. So this thing is going to be the same thing as f prime of a. Now that's nice, but the only way we're going to get somewhere is if we differentiate the right side as well, this other version of the function that we already know. That's what's usually helpful with these. If we already know one thing, we can get the other thing. So on this, we can use quotient rule. First, for quotient rule, first we need to differentiate the numerator. So we'll just leave this right now as derivative of gamma a plus 1. Then we'll just bring down this piece, the denominator minus the reverse, which is going to be gamma a plus 1. Derivative of this is going to be s a plus 1 natural log s. And then what we need is going to be just the denominator squared, all just using quotient rule. Then we need to use some quick algebra. We've got something in common. We could factor it out or do it however you want, but all this is in common. So cancel, cancel, cancel one of these here. And we're getting somewhere, but the confusing part is this, right? Gamma function, the derivative of the gamma function, we usually express, we've got formula, we have a way to express that in terms of an integral, but first it's not really clear how to deal with that. Well, we have a good formula for it though. We have the definition of the digamma function, which is it brings the derivative of the gamma function into it. So this is going to be the same thing as derivative of gamma z over gamma z. But with just a little rearrangement, we can solve for the thing we want. Just multiply by gamma of z on both sides. So then we can bring it on this side. And then what that does is it's going to give us an expression, a different way to do this, where we can actually calculate this, assuming we've got nice input on it. So we'll rewrite this using this. What we get is gamma a plus 1 times digamma a plus 1 minus, again, gamma a plus 1 natural log s over s to the a plus 1. Then let me just clean it up a little bit. We've got gamma of a plus 1 in common, so we can factor that out. Again, if you knew that a was an integer, like if this was like t squared or t cubed, then you could calculate it directly or turn it into a factorial. So in some cases, this is going to be very simple, and in some cases, it's going to be very complicated. But here's what we have left. Just all this stuff here. Now, without knowing what our a and s is, we're not going to be able to like simplify this down to a completely simple expression. In the cases where you know, then you are going to probably get something clean. If it's like integers, I would say. So if we don't know what a is and we don't know that it's an integer, then this here is going to be the best we can do for a formula for this Laplace transform. Now the gamma function and the digamma function can be simplified for some different values that are not integers, but we're not going to really get into that right now. What I want to do is deal with the integer case. So again, like I said, gamma function can be reduced to a factorial. So outside here, we can change this, first of all, to just a factorial. Then for the digamma function, we can use the formulas we have over here to the right, putting it in terms of harmonic numbers. So then what we can do is just use this one right here. Now I also should maybe talk about when a is 0, because when a is 0, we get digamma of 1, and digamma of 1 is just going to be minus Euler-Mascheroni constant, this thing here. So for the a is 1 case, we could just do it out because we'd end up here with just 0 factorial. So we just have a 1 out here. We'd have minus Euler-Mascheroni constant minus ln(s) over this here becomes just s. But this right here, this is just the formula I found in the other video when we did the Laplace transform, just ln(t), which makes sense. T to the 0 is 1. So you could use that for that case just to get back to that other Laplace transform. For other positive integer values, we could use this. And then again, we'll have a factorial here. Digamma of this thing, using this, we can write this as harmonic number minus Euler-Mascheroni constant minus ln(s) over s to the a plus 1. And this is going to be our simplified formula for integer values. And then you can just calculate out, usually, I mean, you're going to want it to usually be kind of smaller numbers, right? Because if you have, like, let's say, the harmonic number of 3, you're just summing from 1 to 3 of this thing. And so this here, this is going to be your formula for integers. This is going to be your formula for real numbers. Okay, so there you go. That's it for today. Thanks everyone for watching. Have a good day.